Welcome to the course on FPGA based signal processing systems. We are doing the synthesis of sequential logics. In that, previously we had the combination logic synthesis, in which we had looked into the latch formation, which is incidental as well as accidental. In the sequential logic, when this synthesis tool synthesized to a flip-flop. So we'll look at this. These flip-flops are synthesized only when the edge sensitive cyclic behavior is mentioned in the clock module. That means always at the rate of passage of the clock or negage of the clock. So that in that sense that the synthesizer identifies this as there is an edge sensitive cyclic behavior, and but not every register variable which is assigned a value in an edge sensitive behavior. Suppose always at the rate passage of the clock or negage of the clock or passage of the reset, whatever the event control expression is. In that, if you have a register which is you are assigning a value to it, not all of them will be synthesized to flip-flop outputs. So let's see that what are the ways in which when this flip-flop will be synthesized. So the case of how does this synthesis tool infer the need for the flip-flop, that is especially when there is a edge sensitive behavior, passage of the clock or negage of the clock. When does the register variable which is assigned value within the edge sensitive behavior automatically synthesize to a flip-flop? That means it will automatically synthesize to a flip-flop or a register or the latch, or how does this happen? The register variable, what is the condition in which it should have? So here we can have we'll answer this also in the with the examples. How does the synthesis tool distinguish the synchronizing clock from the other signal? Suppose you have the passage always at the rate of passage of reset and passage of the clock, so among which the synchronizing signal is clock. How does the synthesis tool recognize that or distinguish it from reset and clock? Okay, so this is the clock and this is reset, just the name is different, reset or clock, passage of the reset or passage of the clock. In that case, how the synthesis tool will know that this reset is not a clock? So those things we will explore today. For example, a variable register, that is a data A, you are assigning a value to it in an edge sensitive behavior, will be synthesized as a flip-flop, and it is referenced outside the scope of the behavior. That means you have to declare that as a reg outside the always block and as an output as well. So output, that should be an output. Okay, so then it will be synthesized as a register as a flip-flop. The output, it is referenced within the behavior before it is assigned a value, or if it is a non-blocking assignment. So exact expression, if that means initializing those registers also will make this register as synthesized to a flip-flop. If it is assigned value in only some of the branches of the activity within the behavior, that means it is not if something the variable equal to data value, or if it is not every condition, it may not occur, but in some of the branches it may the variable may appear. So in those cases also, that would be synthesized as a flip-flop. Only thing is it needs to be declared as a reg outside the always block, and it should be declared as output. So the variable that is referred within the edge sensitive behavior before it assigns a value, that means initializing them in the behavior, will be synthesized into the output of your flip-flop when this is also declared as output and reg. So the cases, suppose for example we took this module, there is an example of input clock, set 1, set 2 and swap, output reg data A and data B. So you can see the input output declarations, wherein these are in single bit inputs and the output always at the passage of the clock. Now if set 1 begin data A equal to 1 and data B equal to 0, end. So once it is else if set 2 begin data A equal to 0 or data B equal to 1. So this is initializing end here. So in this case we can notice that the passage of the clock, set 1 is an input, it is not in the sensitivity list. If set 1 is true, then assign these values. That means in the non-blocking statement it is only going to look at 1 and 0, this is when it is evaluating itself, it is deciding data A and data B is going to be our flip-flop output, assigning a value before it, because this is declared here as output reg and data A and data B. The set as set 1 is happening passage of the clock. It is inherent that at passage of the clock, set 1, if set 1 is this true, then do this operation. So, but explicitly this passage of the clock will not be written over here. If passage of the clock set 1 is 1, then this. So, then the data A, data B is. So, we won't, this is understood, I mean this is from the flow, that if statement will not contain the passage of the clock. Okay. So, if statement assigns a value to data A and data B, and these are non-blocking assignments synchronized to a racing edge of the clock, and which is not explicitly stated in the if statement. So, that is, if statement does not have this passage of the clock over here, it should be noted. Also, if that is initializing the value, if else, what is the condition? Data B is less than or equal to data A, or data A is less than or equal to data B. So, this is end and end here over here. So, else if set 1 and set 2 are not true, then assign this data A and data B. Well, so here this condition will be exercised only if that previous if condition is not satisfied, but data A and data B will be in the synthesis process. But by looking at this here, this would assign the values, or it will declare this as a flip-flop output in the synthesis process. So, that is one, and we have it is a mandate for the flip-flop output to have this data register A, you can see, to declare them as reg and output. So, you have this in the RTL schematic, data A, data B and the data A, this two of them is a flip-flops. So, now it has a passage of the clock, you can see, and data also Q is assigned to this, and then there is a feedback event going to this case set, and data from here, data A, it is going to D. This is a swapping mechanism, and you can see there is a one which is not connected to it. This is declared as input swap, but it does not have any declaration, anything inside the behavior, that is all in the cyclic behavior. So, it is just it is creating a pad here, that is input pin, and it does not connect to the any of the, because it is not used in this. Okay. So, this output declaration needs to be output. Okay, it needs the reg as well as the output. So, the technology schematic, which is for data B register and the data A register, is shown over here, which is taking the clock from here and here, and the chip enable or the clock enable, or we can have the CE for a certain period of time. In the flip-flops we can have this option. So, we will see with some example how the CE can be activated, and the two lookup tables which is giving the swapping mechanism and going to the data and as well as this data. Okay, it takes this input also from here, you can see. Also this one I1 is taking the output from here, that is for the feedback mechanism, because of the swapping problem is the Verilog module addresses. So, here is the technology schematic. We are just looking at this. Yes, at the passage of the clock, even though the clock is not specified in the if statements, it is considered them as the clock, its sensitive behavior in that. Also, the outputs are declared as reg here. So, the lookup table which describes the behavior of this code is given over here, that is the data B and data A. Not, this is a minimized expression, the truth table which is obtained from the cell properties of it. So, the event control expression. So, the next that is the always block, which is having the cyclic behavior. If it could describe this sequential logic, it must be synchronized to a single clock edge of the clock. Clock edge means single clock edge, that is either passage or the neg edge, but not both. The sense you take a decision or the passage of the clock, and not at the neg edge of the clock, because the clock duration will be very small and it may not settle before the neg edge arrives. So, it is better practice to have this code done with the single edge of the clock, which can describe the sequential logic, and not both passage or negage of the clock of the same signal, clock or reset. So, if you use passage of the clock and negage of the reset, fine. Negage of the clock and passage of the reset, fine. Not passage of the clock as well as negage of the clock. So, if you have the multiple always block, it need not be having the always at the rate passage of the clock. Next may be always at the rate some C1. So, these two control expressions which may not have the same clock, but the clock period which almost if you use a passage of the clock and the other signal, if it is better to have the same period which is used in the always block of control expression. The example which we take over here is input clock reset, and input is 4-bit data in and output is 4-bit data out. And let us see this always at passage of the clock or passage of the reset. Begin, have this if reset is 1, data out equal to 4-bit 0, else data out is assigned data in. So, this is a simple code which is having yes passage of the clock or passage of the reset. Okay. So, in this case, how does it decide? This is synthesizer would decide this is the clock and this is not. Okay. So, we can see that every sequential logic, but first better have the if statement for the reset. If reset equal to 1, then data out equal to 4-bit 0. Else, this else condition is synchronized with the passage of the clock, not the reset. So, the reset condition has been taken separately. So, the sensitivity list which contains the passage of the clock as well as the passage of the reset is synchronized to the else statement is synchronized to the passage of the clock. So, the synthesizer decides this is the clock, not this one. So, this is how it differentiates the clock from the other signals in the event list or sensitivity list. So, here if reset, if it is mentioned, then immediately it assigns that this is not the clock. Okay. So, if reset is this, else condition, again else you do not have what is the condition here. So, that implies this is the passage of the clock. So, the RTL schematic for this clock and the data input is 4 bits. So, you can have this 4 bits having the 4 registers, okay, 4 flip flops, yeah. And the reset and the data out is each bit is given a 4-bit. This is each bit is given here combined and giving each of this register output is combined to have the 4 bits. So, if in the technology schematic you can view that in the data input which is going to all the here data input and here data and this is data and then again data input for 4 bits and data output 4 bits. You can see the 4 flip flops for this, else the 4-bit the data will be assigned to the data in will be assigned to data out. So, clock which is having the C, which is the clock is assigned here exactly the same. And so, the reset, so what is over here, if reset assign it to 0. So, this is what the reset, you can see the clear signal here. So, the synthesizer understands that which is the clock or which is the reset if there is an if statement. And the if statement is used for the distinction between the other signal and the clock. So, if we have the again a variable which is having the suppose we in this example input clock, D input and D output and output reg. So, what happens always at the rate passage of the clock we have begin, D in assigned to D out, end. So, here is the case that which is assigned a value in the age sensitive behavior and is reference outside the behavior will be synthesized as output of the flip flop. Supposing you do not assign it as an output or simply saying that there is here is a reg D out, it does not have output. Suppose you do not define this output, then it will not the synthesizer will ignore this and it will not take this as an output at all, and you will be say in the previous the simulators would the synthesizer tool would say that this is having a block which does not have an output, and you will not get the synthesized diagram for it. So, the module input clock, D input, output reg D out. So, it is mandatory to in this, it would give a syntax error if you do the simulation if you don't declare them as reg outside this, but it needs to be output. Okay, so that it can be a flip-flop output. Is the passage of the clock is defined, it is not having any other signal, so it's assumed that this is the clock, passage of the clock, D in is assigned to D out. There is no reset involved in this. So here clock and D input, you can see the clock or D out, which is here D out as a register, D out reg. This is the flip-flop again, the RTL schematic, which is 1 bit, so you don't have the multiple flip-flops. So variable which is assigned a value before it is referenced, but not referenced outside the behavior, will be eliminated in the synthesis process. That means if it won't give you this Q if it is not declared as output, but if you declared as reg not declared as output, then it would be a problem that it should be declared as output and with the reg as well, so that it will not be eliminated by the synthesizer. So the technology schematic here, clock and the clock enable, you will see the clock enable, what is the purpose of this clock enable. Here is D input or here is not mentioned, and the output we get it over here. So that's a standard flip-flop of the technology schematic, which has reset, clock enable, or this one CE, and D is the input which is going to the output. So we need to have this it is to distinguish it from the passage of the clock or the passage of the reset of the, to synchronize the signal which is synchronized to the statements, can be identified by the else statement, if else statement. If else statement is not there, then if you have only passage of the clock, it is assumed that this is the clock, and that passage of the clock what needs to be. So the statement is synchronized with the clock, so it's assumed this is the clock, and data and the clock has been identified, but reset, there is no reset over here, and there is no CE also. So now coming to this FSM, that finite state machines, we had that there are million more state machines. In all these cases, million more, what we had learned is this output logic, how it takes the decision from the input enable. It is only taking the current state. So apart from that, in the synthesis process, we can have them as two categories, explicit and implicit FSM. So the model which we had developed so far, so if you at the rate passage of the clock, to move from one state to another, at the rate passage of the clock, and we say that S next, S reg is less than or equal to S next. So we assign that explicitly, saying that this is the state it is going to move from one to another. So those are and the combinational logic, output and the input, output logic and the next state logic. So there are three of them in the three blocks, if you recall, that FSM has: output logic, next state logic, and the state memory. If you explicitly state that state memory, and always at the passage of the clock, S reg less than or equal to S next. So that is the explicit statement for the state movement, and the combinational and next state logic will follow with the one always statement and the combinational logic. So those category what we had learned is the explicit FSM. Okay, and then implicit FSM. What is that implicit FSM? We'll see there are two categories of state machines: explicit and implicit state machines. So the explicit state machine have one even control expression to make state transitions. That's always at the passage of the clock. S reg is less than or equal to S next, and it also can have the next state logic and output logic. But implicit statement has one or more age sensitive control expression in the behavior, that is multiple always blocks, always at the rate of passage of the clock, or always at the rate of some of the signals. Okay, you can have this multiple ones in case of implicit state machine. That is, we don't specify that this is moving, the state register is not separate. That's what we're trying to say here is as an implicit state machine. And this implicit contain multiple edge sensitive and even control expressions also. If we look at this, the counters and registers, we can say those are the again implicit state machines. So if you have this 4-bit counter, so at each clock event, what happens? The machine executes register operations, and in the code we can see that that it is saving in one register, and then but doesn't make explicit transitions from saying that X next is S reg. Okay, so in the synthesis tool, synthesize a variety of counters and shift register in single cycle implicit state machines. We will see an example of this implicit one. It also completely describes this single control expression, also an implicit state machine. So, if we have the single control expression with a few of them also come under the implicit one. So, we should not be misinterpreting which is implicit and explicit ones. So, the ones which we had seen already, those are the explicit state machines, whereas implicit ones can have multiple always block and one clock edge also. Let us see that. Here, for example, this is a 4-bit ripple counter which has the T flip-flops. Okay, so the clock, you can see this is a ripple counter, so it is understandable that the clock is not same for all the flip-flops. If the first flip-flop has a clock here but reset is same, the second flip-flop receives the clock from the output of the first flip-flop, and similarly second one, third one, and so on. So, the second receives output from first, third receives output from second, and fourth receives output from the third. So, these are declared as count 0, count 1, count 2, and count 3. These are the outputs which we are going to see them in the as a output of the counter. It doesn't have single clock, you can see that. So, in the synchronous, the explicit ones, we have only one clock. Okay, so which is explicit state machine. So, here we have this one clock, and remaining or the output of remaining clocks are obtained from the output of one from the another. Similarly, in the shift registers also we will have such kind of behaviors. If we look at the example of this ripple counter, 4-bit ripple counter which has the T flip-flops and the count outputs 0, 1, 2, 3. T flip-flop toggles if T is 1, the output toggles, otherwise it stays at the previous state. So, module ripple counter which has the input toggle clock reset and the output is 4-bit again. So, in this case the wires are declared here C0, C1, C2, as Q is going as a clock to the next one. Here similarly this part and the C0, these outputs are declared here as wires, because it is not a same clock which is going. There should be a T flip-flop and its connections. As you recall, this needs to be in the structural model. We had learned that this connection needs to be declared as wires. That assigns C0 now. C0 is count 0 and C1 is count of 1 and C2 is count of 2. Okay, so count 3 is the output again. So, the count is the output 0 to 0, 1, 2, 3, which is given C0, C1, C2 here. Always at passage of the reset, passage of the clock. Now, if reset is 1, so you can see the first statement which comes after the always block is reset, so that this synthesizer also recognizes this is reset is the first one, the remaining logic with respect to the passage of the clock. So, if reset is 1, assign this 1 bit to count 0 here, else if toggle is 1 and the count 0 is tilde count 0. The if else if, okay, so, and then we go to the next condition. If reset 1 again, that is with the always passage of the reset or negage of C0. This is here. Again this reset and this clock, we are talking about the negage of C0. This is okay. Passage and negage of C of 0. This is Q, and Q is declared as C of 0, and then negage of that is being used here, so for a negative clock. If reset is 1, then this is assigning this is 0, count 1 is 0, else if toggle the value of count 1 to the previous value to 0, or if it is 0, it count tilde 1 to make it 1. So, this is a separate always block. You can see there was a previous case if else if, okay, and then the next one shows this always at passage of the reset or negage of C of 0. This is also a separate always block, another always block, but it does not take the same clock over here. Okay, the synchronizing clock, as we have said, this it is not the same here. and always at passage of the reset and negate of C1. So, this is the third one. So, in this case we have if, again if statement would give reset count 2 is assigned 0, else toggle is 1 tilde count 2. This toggle this. Else the fourth statement of always 4 flip flops have been always reset or negate of C2 if reset is 1, count 3 less than or equal to 0, else if count 3 is equal to tilde count 3. So, you can have these statements here, that is 4 always blocks, but the clock is only addressing this. This is not the synchronizing signal for all the flip flops. So, the multiple behaviors, multiple always blocks does not have the same synchronizing signal, that one thing, and it is differentiating this clock or this one. Here you can see it is specific to reset and toggle inputs. Okay, this is an implicit state machine, what we call it. Not all of the state registers happening with one single clock. Okay, so it can have multiple even control expression, that even the implicit state machine. So, but it is storing the count 1, count 2 values are getting changed with respect to the clock, but this is storage behavior or storage operations instead of having this state transitions. Okay. So, RTL schematic, which shows the reset, clock and toggle. In that, see that toggle is given as CE. So, clock, passage of the clock, the first one, and the CE you can have this toggle one, and D is the input which is from the register here, and which is equal to Q. Okay, the clear is always the same, the clear you get it same here. So, now the other 3, which is having the negative clock, can be taken from this one, from this Q. You can see the feedback which is coming out from here, one for this, and the next one which is having the feedback itself from here. The clocks are defined, but the D input which is from the, you can see the D inputs, this is decided inside, and the toggle flip flop is the output which is explicitly mentioned here, which uses the D flip flop or inside. So, you can see the thing, and the clock, the toggle is given with the C here. So, the register which is the first one first bit is getting the clock, the remaining, or you can see in this over getting the output from the clock, negative clock is getting from the output of the other flip flops, and this is an example of this implicit state machine. We can also see the technology viewer. First count reg 0, 1, 2 and 3. So, the outputs from one to another are giving as a clock to this, the synthesized diagram. The LUTs which is giving the all the two input LUTs for the count of output 0, and then it takes the what is the output from here to decide what is the output Q0, Q1. Similarly to this, you can see over here which is going, and this one, this output which is also deciding this lookup table, also the fourth one to take the output, making the toggle with respect to the toggle, what should be the output. What to expect, if toggle is 1, then I1, what was the previous state, and that will be made 1. So, here is the operations. If if it is changed, you can see that the output will be 1, 0 to 1 or 1 to 0 transition, otherwise this stays overstayed. This toggle condition is decided. Basically, the registers are over here, and these lookup tables deciding the toggle conditions. So, here I would like to give you the implicit and explicit state machine, the difference between the implicit and explicit state machines, which make explicit transitions are storage operations. Okay, so in this case, the ripple counter is a perfect example. Similarly, the shift registers also can be made as an implicit state machines, whereas the explicit state machines are this sequence generator, what are pattern recognizer, what we had learned, also the Mealy and Moore machines examples. Apart from the synthesizing this, when the flip-flop will be synthesized. Okay, so always that if they see the passage of the clock or passage of the reset, edge sensitive behavior is going to be synthesized as a flip-flop. But among the 2-3 edge sensitive signals are given in the event control expression, how it gets synchronized with this. So that is if statement and else statement. Else statements is synchronized with the other signals. So the synthesizer decides that is going to be the clock, not the reset. So the flip-flop behaviors can be within the always block. If you use the variable that needs to be declared as register, and the same way it should be a flip-flop output if and only then it is declared as output. Otherwise, if you use it, that it is not going to be a flip-flop output, simply declaring as a reg. So with this, we have the flip-flops synthesis, and we'll continue with the registered and unregistered logic of the sequential logics in the coming lecture. Thank you.